So this lesson here will be on optimization problems. When you hear the word optimization, we're thinking to find either the maximum or the minimum of some quantity over a fixed amount. So like maybe finding the maximum perimeter or finding the maximum area or finding the maximum volume or something of that sort, or minimizing the cost. So in this example, this is no different than a grade 11 problem, but we're going to approach it using a grade 12 idea. You could have done this problem in Math 20-1 by using quadratic information. So let's take this question. So it says, find the area of the largest rectangle. So I want to draw a rectangle out. And we know that the perimeter of the rectangle is 200 feet. So perimeter is equal to 200 feet, and we need to find the largest area. So what we normally do is we're given one equation with information, which is called our secondary equation, and we're given one equation that is the one we were trying to maximize or minimize. So here I need to introduce some variables. So I'm going to call this distance x and this distance y, and because this is a rectangle, the bottom would be x and the left would be y. The perimeter could be represented by the distance around the rectangle, so 2x plus 2y is equal to 200. So this is an equation, a secondary equation. It relates x and y together. So what I could do is I could take this equation, isolate for x, and get a relationship with y in relation to x. So I'm going to divide both sides by 2. And this is how y is related to x. Now, when we're looking at this, we want to set up some conditions. We know that x has to be greater than or equal to 0. Y has to be greater than or equal to 0. You're going to see there being a benefit to creating the greater than or equal to and not just the greater than, because we're going to be able to sometimes set up a closed interval. But we also know that since y has to be greater than 0, 100 minus x also has to be greater than 0. So I rearrange this inequality, and I get that x has to be less than or equal to 100. So this is super important to know, because what's happening is I'm relating y to x, and my area of the rectangle is x times y, but that's too many variables to deal with for us. But I know that y is related to 100 minus x, and so I sub that in. Now in this equation, because my x has to be bigger than or equal to 0 and less than or equal to 10, I can set up a closed interval here where I'm required to find a max or min. And so we've already kind of covered this idea. This is called our extreme value theorem. It's the theorem that says you're trying to find a max or min on a closed interval. Your function is nice in the continuity sense. What you do is you take the derivative, you set it equal to 0, find the critical points, and then you're just required to figure out which coordinate gives you the highest and lowest value in this case, and there's always guaranteed to be a max and min. So I take the derivative, is 100 minus 2x. I set it equal to 0, so 100 is equal to 2x, and x is equal to 50. So this is my critical point. Now, when we had learned this a few lessons back, we would want to calculate the area at the end point, the area at the critical point, and the area at the other end point. And when we do this, the area equation that we sub it into is the equation that was simplified with x's in it. So area of 0 is 0, area at 100 is 0, area at 50 is 50 times 100 minus 50, which is 2,500. The largest of these values produces our absolute max, so this is our absolute max. So in this example, the maximum area I can form is going to be 2,500 feet squared, and that will be guaranteed to also have a perimeter of 200 feet. Now, in a given question, when you're solving these optimization problems, the big goal is to try to set up a closed interval where possible on conditions, because in that case, you just need to use the extreme value theorem to guarantee that you're going to have an absolute max and min. Now, if I didn't use the extreme value theorem, I can find local maxes and local mins, but that doesn't guarantee that those are going to be absolute maxes and absolute mins. So in the bottom examples, you'll see that sometimes we have to do a little more problem solving and being a little bit clever to try to prove that these are absolute maxes and mins on whatever interval that is given to you in that case. Now, just the general guidelines for solving these problems. You want to kind of look at the information in the question, figure out what quantities are given and what you want to find. And when you're doing that, you want to do that in a way where you're taking the information in the question and turning it into variables and symbols. Okay, so let's just write here. Try to use symbols. And then when you're taking the information, turn those oral information into variable mathy type information. You're usually going to get two types of equations. You're going to get a primary equation, which is the one that you're trying to maximize or minimize, and we want that to only have one variable in it. Okay, so it'll be the variable that you're trying to maximize or minimize, and then one variable on the other side. The secondary equation is used to sometimes help us turn that primary equation into having only one single independent variable. Sometimes if you're not given a secondary equation, that means you're able to find an equation with only one independent variable. You want to come up with a feasible domain. If you're able to set up a domain that has a closed interval, you can use the extreme value theorem. Otherwise, you're going to have to do your max and min using calculus, and then you need to somehow prove the global max or min based on the local max or min. Sometimes we can do that just through limits, but again, sometimes a justification is necessary. Now again, these problems can vary in difficulty. We're going to start with some of these simple shape type problems. You can see the heading here says to find the maximum volume, but let's just kind of read the example. A manufacturer wants to design an open box. It's important to know that the box is open because when you're thinking of surface area, it changes the relationship when you write the surface area. We know that it's going to have a square base, and we know it has a surface area of 108 square inches, and we want to find the dimensions of the box. So let's use the orange. So we need to find dimensions of the box that will produce a maximum volume. So we know that this is an optimization problem because we're trying to find a max or min. Okay, what are we trying to maximize? We're trying to maximize the volume. So the volume will be my primary equation. They give me information about a surface area, so that's going to be my secondary equation. They've already described variables for our box. They label the bottom of the box using x by x because it's a square, and then the height of the box is h. So my surface area equation is going to be the area of the base, which is x squared, the area of the front and back, which is 2xh, and then the area of the two sides, which is 2xh. So in this case, my surface area is x squared plus 4xh. And this happens to be this formula in this case because we have a square base, but sometimes the sides can have a different relationship than the front and back. And then because we have an open top, we don't need another x squared for the top. We just need the surface area of the bottom, which is 1x squared. My volume is base times length times height times width, whatever the three dimensions multiplied together. So I'm going to get x squared times h. Now you're going to notice that the one we're trying to maximize has two variables there, and we needed to have one independent variable. So we're going to use our surface area equation to get this down to one independent variable. You want to ask yourself which variable is easier to solve for, and there's a single h in there, so I'm going to isolate for h. So I'm going to subtract x squared on both sides, and then divide both sides by 4x, and I get h. Now let's think about what needs to be true for my box. We know that x has to be greater than or equal to 0. And again, if you're able to create the equality, that's better. We know that if x is 0, we wouldn't have a box. But again, if you're able to set it up using a closed interval, it's better. Now, h also has to be positive, but now because I have an expression for h, this expression also needs to be positive. So this is sort of a rational inequality. We talked about how to solve this inequality by taking the zeros of the top and bottom. So plus or minus root 108 is the kind of the x-intercepts of the numerator, or the critical points of the numerator. The critical point of the denominator is 4x. We're only interested in x and h greater than 0, so I'm going to make that greater than 0. So we want to test the signs in my h function to figure out, is this inequality true or false, or positive or negative. So if I take a number like 1, I sub it in here, I'm going to get a positive h value. And when h is like bigger than square root of 108, the numerator is going to be negative, so therefore the entire expression is negative. So because this h needs to be positive, we need to stay within 0 is less than or equal to, and this should be the x because that's the variable I'm dealing with when I'm doing the number line. So x has to be between 0 and square root of 108. Now again, because I'm able to set up my problem on this closed domain, and here's my volume function, it makes it simple because now when I'm trying to do the problem, I just need to find the critical points and use the extreme value theorem. So my volume equation is given by x squared times my h function, which is 108 minus x squared divided by 4x. I'm going to simplify this volume equation. So I'm going to take out an x out of both the top and bottom and distribute my formula out. So 108 divided by 4 is 27. So this works out to 27x minus x cubed over 4. That's my simplified volume equation. Take the derivative, 27 minus 3x squared over 4. I set my derivative equal to 0 or undefined to find critical points. So this is going to be 27 minus 3x squared over 4 is equal to 0. 27 is equal to 3x squared over 4. 108 is equal to 3x squared. Divide both sides by 3 is 36. X squared is equal to 36. When I solve that, x is equal to plus or minus 6, but again, x has to be greater than 0. So x is equal to 6. So I have one critical point, volume at 0, volume at 6, volume at square root 108. I sub that into my volume equation, which you can use whichever one you want. I'm going to use this one right here. Now when you sub that in and test it, the volume at 0 is going to be 0. The volume at 6 is going to be 27 times 6 minus 6 cubed divided by 4, which is 108. And the volume at square root of 108 is, we take 27 times x minus x cubed divided by 4, and you get 0. So again, this represents my absolute max, because it's the highest number I get. Okay, so what are my dimensions? So we're going to just kind of summarize that the dimensions are 6 feet, or inches. So that's my x. And then my other x would also be 6 inches by, and then my h would be, let's just write it here, h is equal to 108 minus x squared over 4x. When I sub that x is equal to 6 in, I get that h is equal to 3. So my dimensions of the box are 6 inches by 6 inches by 3 inches. And we know that this is the absolute max because we're using the extreme value theorem to prove that. Now again, example 2 is another really popular example. This one's a little bit harder to recognize that they're asking you optimization, but they say what points on the graph are closest to the point 0, 2. The fact that they're saying closest means we want to minimize the distance between the point 0, 2 and the point on the curve, 4 minus x squared. So what do? We draw the curve. We know it's a parabola. It opens down because the leading coefficient is negative. And then using our transformations, it moves 4 units up, so it's my parabola facing down. There's going to be a point on the curve. In this case, because the curve is symmetric, there's going to be 2 points on the curve, which they've labeled kind of x, y for now. But when we solve for x and y, we're going to get 2 answers. And what we do in this example is we want to set up a distance formula between the point x, y and the point 0, 2. So from grade 10, you know that the distance between 2 points is y minus the y coordinates squared plus x minus the other x coordinate squared. Now you're going to notice that this equation has 2 unknowns in it, and we want it to only have 1. But what do we know about this function y is that that point sits on the curve 4 minus x squared. So I'm allowed to take that curve and sub it in for y. So 4 minus x squared is my y term. Let's just highlight that so you can see that. Minus 2 squared plus x squared. And one more cleanup step. So 2 minus x squared all squared plus x squared. That's my function that I'm trying to optimize or minimize in this case. So this is my primary equation. We don't need a secondary equation, but if we did, this is sort of our secondary right here because it gives us more information how y relates to x. Once you have your primary equation, you would need to take the derivative, but in this example, there's no restrictions I can set up because the points are allowed to be positive and negative. So now we're kind of stuck trying to prove that this is an absolute max versus a local max. So to find the answer, we need to take the derivative and find critical points because those are the points that will be potential local maxes and mins. So this is going to be chain rule. We have something to the power of 1/2. We're going to do 1/2 something to the power of negative 1/2. So this is going to be the square rooted term on the denominator. And then we need to do chain rule, which is the derivative of the inside. So I'm going to do 2 times 2 minus x squared to the power of 1. Derivative of the inside is minus 2x. Plus the derivative of x squared is 2x. So here's my derivative. We're going to clean it up. I'm not going to do anything to my denominator. Numerator I'm going to distribute out. So 4 minus 2x squared all times negative 2x plus 2x. Now instead of distributing this out fully, what I'm going to do is I'm going to notice that both terms on the numerator have a 2x in them. So I'm going to factor out a 2x on the top. So I take out a 2x. What am I left with? I'm left with this negative sign. And 4 minus 2x squared plus, and then there's nothing left from that term, divided by 2 square root 2 minus x squared all squared plus x squared. Let's continue cleaning up the numerator. So 2x, I get positive 2x squared minus 4 plus 1 is minus 3, all divided by the square root stuff. 2 minus x squared all squared plus x squared. Now you'll notice that denominator and numerator both have a 2 out front, so I'm just going to cancel that out super nicely with my handy dandy eraser tool. So we want to set the derivative equal to 0 or the derivative undefined, but I want you to take a look at the bottom. The bottom has an expression here that's something subtracted squared, so that's a positive expression. And this is a positive expression, and then you take the square root of it, the bottom is always positive. It will never be able to equal 0 at all. So now the numerator equaling 0, d prime equals 0, implies that x can equal 0 or x can equal plus or minus root 3 over 2, all under the square root. Let's just extend my square root when you isolate for that second term. So 2x squared minus 3 equals 0. 2x squared equals 3, and then again you keep isolating for x, and that's what you get. Now in this example, we're going to have to continue by drawing my number line and continuing with that curve sketching, sort of increasing, decreasing process. D prime goes on here. I'm going to have negative root 3 over 2, 0, and positive root 3 over 2. And then I'm going to check the signs into my simplified derivative function, which I'm going to circle here for you. Now the numerator or denominator is always positive. What about the numerator? I sub in like negative 7. I'm going to get a negative answer from the x, and the other piece is going to be positive. I take a number like negative 1. Well, what is root 3 over 2? Square root of 3 divided by 2 is 1.22. So this is approximately negative 1.22. So if I sub in negative 1, I get a negative, and then another negative, which makes a positive. And you continue carefully working out the signs like we did in curve sketching. And what does this tell us about the original function? It's decreasing, increasing, decreasing, increasing. So if it goes from decreasing to increasing, there's a local min at negative root 3 over 2 and some y coordinate, which I don't know at the moment. And then there's another negative to positive sign switch. So there's another root 3 over 2 and a y coordinate for that point. So they're both local mins because d prime switches from negative to positive at that point. So these are my local mins, but are they the points closest? We don't know, but on the graph there's only 2 critical points. We just need to make sure that there's nothing else that kind of goes lower than those 2 low points. Now when I actually prove this, what I could do is I could take the limit as x approaches infinity of my d function, which is 2 minus x squared plus x squared. So I'm doing 2 minus a large number squared is a negative large number. I square it, I get another large number plus a large number. Square rooted is a large number. So that's telling me as my d function goes to infinity, the graph is going up. When I do the limit as x goes to minus infinity of 2 minus x squared plus x squared, by the same reasoning, this is going to give me plus infinity, which means that the graph is going up at the negative infinity end. So these local mins have to be absolute maxes and mins because there's no other critical points and the graphs are going to infinity. So I'm going to say therefore Negative root 3 over 2, we'll find those y coordinates in a minute. Positive root 3 over 2, and that y coordinate will be my absolute min. So therefore, they're the closest points. How do we find those y coordinates? We just sub them into the square root of 4 minus x squared. So y is equal to 4 minus x squared. So if I square root 3 over 2, I get 4 minus 3 halves for both scenarios. And 4 minus 3 halves is going to give me 2.5. So this y coordinate is 2.5 in both cases. So those 2 points are the closest, and you can see that one is on the right hand and the other one's symmetric on the left hand side.